Here, I would like to look at the domain of a log function. But before we do that, we have to talk for just a second about a normal convention we use for log functions. So if we have that a is not included in log base a of c is equal to b, then we usually assume that a is equal to 10. This is because log base 10 is usually the most common log function you're going to see. So if we don't see a present at all, that means a is equal to 10. So we'd write this just as log uh, of x is equal to 10, right? We would just assume that a equals 10, right? That's just an example, okay? So we would have log base 10 of x is equal to 10. That's how we would read that, okay? But we also want to see a little bit more detail why the c value in our log functions for log base a of c is equal to b. Why does c always have to be positive? Well, if you remember, we said a is always positive, okay? And log base a of c is equal to b if and only if a to the b is equal to c, okay? So, since A is positive, that means that C will always be positive, okay, regardless of what value from negative infinity all the way to infinity B takes on, okay? To see this, let's let A be 2. So if we have 2 to the B is equal to C, let's see why C always has to be positive. So for B equals 1, obviously, we have 2 to the 1 is equal to, well, 2. Okay, that makes sense. Uh, for b equals 2, we have 2 to the 2 is equal to 4. Okay, we can keep going off. Obviously, this is going to get bigger and bigger and bigger. We can 2 to the 10, 2 to the whatever. We can go as high as we want, and it's going to get bigger and bigger, faster and faster. And so, obviously, that will stay positive. What if we go to negative numbers? So if we have for b equals -1, we get 2 to the -1 equals 1 over 2 to the 1 equals just 1 over 2. So we get 1/2. For b equals -2, we get 1 over 2 squared, which is 1 over 4. So what we're going to see as we go more negative, if we get more and more negative numbers, like further to the left of 0 on the number line, um, that means that we're going to get closer and closer to 0. But we still are going to remain positive. So it's going to get really really small, but it will still stay positive. Okay, so this is really helpful when it comes to solving domain issues for log functions. So here we have f of x is equal to log of x squared minus 9. Okay, let's go ahead and see what the domain would be for this function. So we need x squared minus 9 to be greater than 0. And again, this is because c has to be greater than 0 for a log function. Okay? So, if you think back to our previous inequalities, we can check that x squared minus 9 can be written as x plus 3 times x minus 3. Okay? So, if we want to think, we can check all of our zeros, right? We can check if you'd like to do this, you can feel free to confirm me on this here. If we were to make our little chart where we have each of our zeros and we take test values from each interval, we're going to come up with the interval where this is positive is going to be from negative infinity to -3, union with 3 to infinity. And this is pretty easy to check if you just look at x squared minus 9. If you pull, say, -4, we'll have x squared minus 9 would be -4 squared minus 9. So 16 minus 9, obviously that's positive. And then obviously the same thing for +4, it would be as well. But if you pulled, say, 2, something that's not in this interval, we would have 2 squared minus 9. So 4 minus 9, that's negative. So this would be our interval we can pull from for the domain of our function f of x. Okay, let's take a look here at this one. How about g of x equals log base 2 of 9 over x plus 6? Okay, so here we have 9 over x plus 6 must be greater than 0. Must be greater than 0. Okay? So, really, one thing we can note here right off the bat is that the since the numerator is positive, the numerator 9 is positive. We need to make sure that the denominator is also positive. Okay, so you can actually further simplify this as x plus 6 is greater than 0. And to see why this is, if x plus 6 was not greater than 0, then it would become negative. That would be the only time that this expression would be negative, is if x plus 6 was less than 0. So we need x plus 6 to be greater than 0. So we can take 6 away from both sides, and we get x greater than 6. Or we can just write this as 6. I'm sorry, x greater than negative 6. So we would actually have negative 6 to infinity. These are all of the values that would make sense here. So to test this, you could pull, say, 0. If you plugged in 0 for x, we would get 9 over 0 plus 6, which is 9 over 6, which is positive. So we'd be good. So this is the domain for our log function here. One thing that you may be noticing so far is this base value here actually doesn't matter at all in the way we're defining this. Okay. Only thing we need to worry about is that c value is greater than 0. So don't get hung up too much on how the log function is constructed, or whether or not it's a natural log or whatever, whether it's base 10 or not. The only thing that matters here is the c value is greater than 0. This last one here, just for fun. Here we have log of x squared plus 4 is greater than 0 to find our domain here. So we have x squared plus 4 is greater than 0. And maybe this would be helpful to see. You can hopefully just see this fairly quickly here. If we if we looked at any value here, this will always be positive. And the way we know this is any value you square, whether it be negative or positive, 0, it doesn't matter. It will always be a positive number. So we know that since x squared is always positive, okay, then x squared plus 4 is always positive. Okay, so and this is because you're adding 4 to it. So if you add 4 to any positive number, you're going to get another positive number. So since x squared plus 4 is always positive, that means we can plug in any real number here and it will make sense. So we have from negative infinity to infinity.